Hey, Harsh here. Every single application you use, from social media to banking to gaming, has a database working tirelessly behind the scenes. But what exactly is a database and how to choose the right one? This kind of isn't a one size fits all problem. The choice of a database is one of the most critical decisions in system design, impacting your application's speed, reliability, and ability to scale. Let's start with the absolute basics. What is a database? At its heart, it's just a structured and organized collection of data. But the magic is in the software that manages it, called a database management system or DBMS for short. Think of it as a library is a database of a huge collection of books. The librarian is the DBMS. You, the user, doesn't just wander into the stacks and grabs the book. You go to the librarian and say, okay, hey bro, I need a book about system design. The librarian knows how the library is organized and finds you a book. The DBMS does the same for your application's data, ensuring everything is handled efficiently and safely. When we say MySQL or MongoDB, we are usually talking about DBMS. Before we write a single line of code, we must design a database. This is the blueprint phase, which is extremely important. The goal is to create a structure that keeps our data accurate and then is fast to access and can handle growth. The design process starts with identifying three things. First, entities. These are the main nouns in our system. For an e-commerce site, that would be things like user, product, and order. Each of these things will likely become a table in our database. Second, attributes. These are properties of our entities. A user has a name and an email. A product has a price. These are the columns in our tables. And third are the relationships. This is how the entities connect. A user places an order contains products. Defining these relationships is key to a good design. Broadly, the database is split into two major philosophies: SQL and NoSQL. SQL databases, also called relational databases, have been standard for decades. They think about data in terms of tables, rows, and columns, just like a very strict set of interconnected spreadsheets. The top priorities are structure, data integrity, and consistency. On the other hand, we have NoSQL, which stands for not only SQL. This is a newer, more diverse family of databases. They were born out of the need to handle the massive volume and variety of data from model web applications. Think Amazon, Facebook. Their priorities are massive scale, speed, and flexibility. And now we are even seeing more specialized types emerging for AI and real time data. We'll cover those soon. Let's dive into the SQL world. Here, everything is about tables. To connect these tables, we use keys. Each row gets a unique primary key, like an ID number. When we want to link tables, we use a foreign key. The book table has an author ID column. That's a foreign key that points to the author ID in the author's table. This is how we know that the Harry Potter was written by J.K. Rowling. This structure enforces data integrity. You can't add a book with author ID that doesn't exist in author's table. SQL databases are famous for being ACID compliant. This is a set of guarantees that make transactions reliable. Think of a bank transfer. Atomicity ensures you can't withdraw money from one account without depositing it in another. Durability means that once the transfer is complete, it's permanent, even if power goes out. This reliability is why SQL powers most financial and transaction systems. So, if SQL is so great, why do we need NoSQL? This is because the nature of data has changed. We started dealing with messy, unstructured data at a massive scale. SQL databases are great at scaling up, making a single server more powerful, but they can struggle to scale out by distributing load across many servers. NoSQL databases were built from the ground up for horizontal scaling. Need to handle more traffic? Just add more machines to the cluster. This makes them incredibly powerful for large scale applications. But NoSQL isn't just one thing, it's a family of different database types, each with its own strengths. Let's look at the main categories. First up, key value stores. This is the simplest NoSQL model. You have a key, which is a unique identifier, and a value, which is the data. That's it. Because of this simplicity, they are insanely fast. There is no complex query language, you just ask for the data associated with the key. This makes them perfect for caching. Instead of hitting your main database for frequently accessed data, you can just store a copy in a Redis cache. The next time a user requests the data, you can retrieve it from Redis in microseconds. They are also widely used for storing user session information. Next are document databases. Here, data is stored in flexible, self-contained documents, most commonly using a JSON-like format. Think about a user profile. If it has a username, email, maybe a list of interests, and a nested address object in a document database, all of this information can live together in a single document. This is very intuitive for developers because it maps directly to the objects in their code. Because all the related data is in one place, you often don't need to perform joins, which can make reads very fast. This flexibility is perfect for things like product catalogs, where different products might have very different attributes. Column family stores are the heavyweights of NoSQL world. They are built to handle truly enormous amounts of data. While a SQL database stores data row by row, these databases store it column by column. This structure makes them incredibly efficient at aggregating data across many records. For example, if you want to calculate the average temperature from billions of IoT sensor readings, a column family store would be extremely fast because it could just read the temperature column without having to process all the data in each row. This is the kind of database that powers large scale event logging, analytics engines, and messaging platforms. Finally, we have graph databases. These databases don't just think in terms of tables or documents, they think in terms of nodes and relationships. This is perfect for data where the connections are just as important as the data itself. Think about a social network. You have people as nodes and friendships as edges. A graph database makes it trivial to answer questions like find me all the people who are friends with my friends but aren't my friends yet. Doing that with joins in a SQL database would be an absolute nightmare. This power makes them a go to choice for recommendation engines, fraud detection by tracking relationship between accounts, and complex social networks. One of the new innovations in NoSQL has been time series databases. With exploding IoT and observability tools, traditional databases choke on timestamp data because it is append only and queried by time ranges. Time series DBs are purpose built, they ingest data at blazing speeds, compress it efficiently, and let you slice it by time, like calculating hourly averages from a year's worth of servers logs in seconds. In the recent years, with edge computing everywhere, these are essential for real time monitoring. And if you are into AI, which who isn't, I guess, vector databases are the new kid on the block. They store embeddings, those dense vector representations from models like GPT, and excel at finding similar queries. Imagine a Netflix recommendation system. Instead of keyword matches, it finds movies whose plot vectors are closest to your watch history. They are the engine behind modern intelligent applications. So, which one do you choose? With these emerging types, the choice gets even more nuanced. Time series for anything time bound, vector for AI smarts, but the principle holds. Match the tool to the data, it always depends on your use case, like for everything in system design. The rule of thumb is you use SQL when your data is structured and you absolutely need data integrity. Use NoSQL when you're dealing with massive amounts of unstructured data. You need extreme write performance or your data model is constantly evolving. For AI/ML workloads, layer in vector DBs, and for real-time metrics, use time series. One more thing before we wrap up. If you love SQL structure but need NoSQL scale, check out NewSQL. These are distributed relational databases that feel like traditional SQL but run on clusters. They're gaining traction in these new years for enterprises migrating to cloud without rewriting everything. Worth exploring if your app starts simple but grows huge. The final and the most important takeaway is that modern applications embrace a concept called polyglot persistence. It means using multiple databases, each for the task it's best at. A modern e commerce site is a perfect example, using half a dozen specialized data stores to deliver a fast, reliable, and intelligent experience. The goal isn't to find one database to rule them all. That is wrong, but Postgres is kind of doing it. It's important to understand the strengths and weaknesses of each type, analyze your application's need, and build your system using right combination of tools. For example, in an e-commerce website, You would have a SQL databases for managing core user accounts, orders, and payments. But you would have for product catalog a document DB like MongoDB. For caching, you would have Redis. And for log user activity, you would have time series databases. For product recommendations, you would have vector DBs, and you would have a search engine like Elasticsearch for product search functionality. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.